Good morning, folks, and welcome back to Week 12 of Building Construction for the Fire Service here at Madison College. This week you're going to be studying about roofs, and roof structures are important to the fire service. Number one, because roof structures represent long spans, and if you read some work of structural engineers that kind of comment on this stuff, Mario Salvadori comes to mind. He talks about how structures don't get interesting until they have to do something substantial, like go to a great height or span a great distance. And roof structures, as they're constructed today, are long span structures in the sense that if you think about floor joists in a house, we may have a beam running down the middle, and the floor joists might span half the distance between the foundation walls. But far and away, what's most typical in terms of roof structures today is that they span from outside wall to outside wall of the structure with no intermediate support. So your average roof structure truss is spanning about twice the distance of your average floor structure floor joist. Other reasons that roof structures are important to us is that we spend time on the roof as part of our mission in structural firefighting. And I don't want to get a lot into tactics in this class. That's probably better discussed in Fire Academy class or in the strategy and tactics class. But suffice it to say that we find ourselves on the roof from time to time for the purposes of ventilation. And we should understand how roofs fail so we can operate safely there. Finally, another reason to be concerned with roofs is that when a building's charged with smoke and we're in there working, either searching for victims or trying to find the fire to do suppression, typically it's charged with smoke from floor to ceiling, which means we have very little opportunity to inspect the structure above us. NFPA did a study, a 10-year longitudinal study about firefighter fatalities relating to roofs, and what they found was that about 80% of fatalities caused by roof collapse were actually firefighters that were inside the building. In other words, the roof snapped through and crushed the firefighters below as opposed to the firefighters on the roof falling through into the fire, although that really does still happen too often. You've all had an opportunity to watch Chief Vincent Dunn's video about operating on peaked roofs, and I think there were some really good comments there from Chief Dunn. So here you're going to see now the associated workbook chapter with that's going to talk about some of the technical details of roofs. Before I talk about the NCST paper for this week, I'd like to show you a short video clip that reflects some of the hazards associated with working on the roof. So what you're seeing here is a flat roof in a Class 3 ordinary type construction building. And remember that a Class 3 type building is masonry load-bearing walls and wood roof and floor assemblies. The way they make this roof waterproof is that there's a rubber membrane, which you can see in this picture, that is stretched over the roof, and then even though we call it a flat roof, there is a slight pitch to it, and the water runs by that pitch. Buildings in this part of town, in the Business Central District, are on what we call zero setback lots, which means one building touches the next. And you can actually see that here, that there's what we'd call a party wall here, a shared wall between the two buildings, and the two buildings actually touch each other. Now this highlights one of the hazards with sounding the roof. If you think about sounding the roof, really what you're determining is the integrity of the roof sheathing, the oriented strand board, or maybe if you're lucky, plywood that covers the trusses. Sounding the roof tells you nothing about the truss structure itself below. And what you're going to see here is a bottom chord failure of a parallel chord truss. So this was not the sheathing of the roof failing. This was the actual loss of tensile strength in the bottom chord of the truss due to the burning action of the fire. Now, these firefighters got extremely lucky, and somewhere there's a roofer that really did their job putting down this rubber membrane, and wherever that roofer is, there's 4 firefighters that can thank him for their lives. So you can see they're working to do the ventilation here. Now you'll notice they did not fall through the roof. What happened was the entire roof truss actually failed. The roof fell down, but what really held things together was that rubber membrane for a few minutes, and here they're able to bail out over the associated parapet wall there. That's about as close as you come to die in on the job and living to tell about it. So a really high-risk operation to be up on that roof like that. Now I want to just briefly diagram what I was talking about in terms of truss structure. So if you think about a typical wood frame residential truss roof, you have an exterior load-bearing wall out on the side and another exterior load-bearing wall out on this side. And then you have this triangular shape, and across the bottom of the triangular shape we have this bottom chord, which is in tension, and we have top chords which are in compression, and then we may have some intermediate webbing that simply acts to prevent bending loads on the top chords. There we go. Right, we'll have a king post, oops, we'll have a king post here, and then we may have some intermediate webbing that is just simply there to prevent bending loads on this top chord up here. By definition, a truss is a structure that's loaded purely axially, which means that these top and bottom chords and these intermediate webbing, the force acts along their axes. They experience only pure tension or pure compression. There are no bending moments. Now, in reality, we know that no roof structure really ever meets that, but we treat it as though it is loaded that way. So if you think about what you've been taught in the academy about working on this, right? You ladder this thing from the side, and before you step on it, you sound the roof down here on this end. Well, part of the problem is here you've got two chords coming together, great big giant gusset plate, and you're right above the supporting structure of the roof. This down in here, this is the sturdiest part of the roof. And in your career you will see buildings where this entire roof has burned off between these kind of squiggly lines here, but these ends will remain. So sounding the roof right here does not tell you a heck of a lot. Then you sound as you work your way towards the peak, and yes, sounding is going to tell you something about the condition of this sheathing along here. But if you think about what happened in the video we just watched, this span is long, right? In a typical house, probably 25 to 30 feet. They're not going to get a 30-foot long 2x4 to make the bottom chord of this truss. That's just too expensive of a piece of wood. So what you have here is you have a gusset plate here. In fact, realistically, with a span of that length, you've probably got some more intermediate bracing here to prevent bending loads. You got another gusset plate here. You got another gusset plate here. And as the fire works to heat that gusset plate, at some point it's going to give up, and this roof is going to fail in tension. And this end of the roof is going to go this way, this end of the roof is going to go this way, and the whole roof is going to snap through like this, right? So that after one of these gusset plates fails, this roof will have taken on a shape like this. Well, this is problematic for a couple of reasons. Typically it'll snap through and it'll hit the floor below. One of the problems is that if you're working down in this region, the roof just fell on you. And again, under the NFPA study, this was the this was the kill zone. This was the most likely area to be killed by a roof, was actually where it snaps through and falls on you. The other thing is if you were standing on this flank of the roof, now you're going to slide right into the fire. Really highly hazardous, and the problem is this gusset plate, we have basically no mechanism to inspect. The moral of the story is if you get any fire at all above this ceiling plane, if there's any fire in the attic, you really got to stay away from this thing. Don't crawl underneath it. Don't go on top of it. If there's a fire in the attic, there's really no sense of being on the roof, because that fire is going to burn a hole through the roof in a couple of minutes anyhow, and why risk your neck to cut a hole that the fire is going to develop for itself anyhow. Realistically, if the fire's up in this roof structure, the structure is likely a goner anyhow. This is very expensive to repair. The insurer is just going to opt to start over with this building. So just food for thought on sounding the roof, the value of sounding the roof, and the limitations of that approach. Now, the last thing I wanted to talk about was the NCST paper. So last week you were working on developing proximate causes, and recall that proximate causes were those causes that were most directly related to the failure. And when we looked at this last week, we said that this is a section of the World Trade Center. We have these large spandrels on the outside and long exterior columns. And the long exterior columns were braced to the interior columns by this floor truss assembly. And remember what happened with this is that if we think about a column is an interesting thing in that as it gets longer, it gets weaker. So here's a column of some effective length. And if it's braced in the middle, like let's say this is 20 feet, if it's braced in the middle, it acts like two 10-foot columns. And that matters because the strength of a column, you might think that a column gets weaker like 1 over its length, right? So the strength of the column, the compression strength of the column is approximated by some ratio of 1 over its length, but it's actually not. The strength of this column in buckling varies by 1 over the length square. And the guy who figured this out was a guy named Leonard Euler. And you'll still, if you read about structures today, you'll read about Euler's columns. He's the one that developed the mathematical model that approaches this. And I know you look at his last name and you say Euler, like Ferris Bueller, but it's not. It's Euler. That's the way he pronounced it. And herein lies the issue: is that if you lost this floor joint here, these two 10-foot columns now become a single 20-foot column, and its strength is not half as strong in buckling, right? In compression by buckling, now it's 1/4 as strong. So losing that floor joint was absolutely critical, and losing that floor joint we would call the proximate cause of the failure. Now, what were some contributory causes? Well, if you think about kind of why did the let's just do a little fishbone diagram here. We had a loss of the floor joint. Well, what contributed to that? Well, the big one was the sagging of the truss. There were probably some other ones that were contributory. The joint design, right? They had designed this as a bolted joint, mainly for cost savings. Had that been a welded joint, there might have been a different outcome in terms of loss of these. Well, why were these floor joists sagging? Well, they were sagging because they got too hot. But why were they too hot? Well, because they had lost the spray-on fireproofing. So you could ask, well, why did they lose the spray-on fireproofing? Well, the spray-on fireproofing was not robust to the type of impact from an airplane. Basically, as the aircraft came through here, it disintegrated, and the little shards of metal sandblasted all of the spray-on fireproofing off of these floor trusses. Well, why wasn't it robust to that type of event? Well, because no one had ever contemplated the possibility of a aircraft crashing into this building and stripping off all of the fireproofing. Now, there are a number of other contributory causes, but I don't want to belabor the point here. The moral of the story is that with contributory causes, there are somewhere between those proximate causes, which were the immediate cause of the building failure, and those root causes, those kind of systemic things that far back, many steps removed from the failure, happen. It's somewhat arbitrary to make a division between proximate and contributory and root causes. So you just have to make your best judgment call as to what's kind of the middle of the road, those kind of medium length causes. And that's what you're going to write about for this week. As always, if there's anything I can do to assist your learning with this week's content, please feel free to get in touch with me at the contacts listed in the syllabus.